Okay, so time to start. First part, what is molecular imaging? If you look a bit up on Google, what you find is that it's a biomedical discipline that enables the visualization, characterization, and quantification of biological processes taking place at cellular and subcellular level in living subjects. So we are at the level of at cellular and subcellular level, and we can measure this in vivo. And it's not just about visualization, but we can really quantify the biological processes of interest. If you go on Wikipedia, quite surprisingly actually for me also, is that molecular imaging comprises many different things. Magnetic resonance imaging actually is also molecular imaging because we are still measuring molecules. But today we will focus on positron emission tomography, which is a technique that has a very huge sensitivity. We have a sensitivity for to detect the biological targets of interest in the nano to picomolar range, while MRI, in comparison, it's in the millimolar range. So we are several orders of magnitudes more sensitive. Positron emission tomography is a technique based on radiotracer that we inject in the subject to image the molecule of interest. What is a radiotracer? Well, it's a ligand which is labeled with a radioactive isotope. So essentially the tracer is made, the radiotracer is made of two parts. One is a molecule, or something, let's say, very, very similar to the molecule of interest that has the same metabolic behavior as the molecule of interest. And this molecule of interest is bound to the isotope, which is what allows us to measure the molecule of interest in the system, which is called a tracer because we just trace the process of interest without altering it, because we inject in very, very small quantities. So how does it work? If you want to do a PET scan, well, you need to first get your isotope of interest, which is an isotope that is emitting positrons. Then you have to bind your isotope to your molecule of interest to obtain a tracer. So to do this, you need normally a cyclotron, but many tracers can now just be ordered from the industry, so you don't need necessarily to have a cyclotron into place. For some tracers, you just order them, and if you have a PET scan, you can pretty much do your acquisition. So you get your tracer, you inject your tracer in the subject, and then either immediately or after a certain time interval, depending on the tracer, you put the subject into the PET scanner and you do your measurement. How your measurement works is that your tracer will bind to the target of interest, and once it's there, the tracer is decaying, is an active isotope. Its decay will emit a positron, which will travel for a few millimeters until it encounters an electron. And when this happens, matter and antimatter annihilates, right? And so we have two gamma rays at 511 kiloelectron volt of energy that are emitted at 180 degrees, and we detect this coincidence. So these gamma rays emitted at the same time in the expected positions are emitted by this ring of detectors. And then with a lot of physics and recognition of coincidences, we can reconstruct our images. We can also, it's not always done, but for some tracer, we also get some blood sampling during the PET scans, and this is necessary in some cases for quantification, as Alessandra and the others will explain more later. A very important point I would like to make, because last year I was speaking with somebody at OHBM and realized there is a lot of misconceptions about positron emission tomography. I would like to explain what is not positron emission tomography. And to do that, I would like to start with a question. So I don't know if many of you, I guess, are familiar with these concepts: functional connectivity, default mode network, resting state connectivity, and connectome. Everybody familiar with this? Yes, guys, pretty famous stuff. So my question for you is, how many of these concepts were developed and or established first based on positron emission tomography data? Okay, it's a bit a suspicious question, right, because we are in a course about positron emission tomography, but I would like every one of you to pick a guess. So how many of you would say that all these four concepts were developed based on PET? Who wants to raise their hand? Okay. How many think 3 of these concepts? Okay, how many? 2? Okay, 1? Okay, 0. It's possible. No, 1. Okay. So my best answer to that actually is 2, in the sense that functional connectivity was proposed based on perfusion PET data, and the fault mode network was discovered based on perfusion PET data. Resting state MRI is what made us think about resting state connectivity, and the connectome was proposed for structural MRI. So just the concept for me is that PET is something that is an old technique, of course, but it's something that has a huge current impact on the field of brain mapping, as these concepts is still things we are working on right now. The second point I would like to make is that this old technique has not been entirely replaced by fMRI, so PET is not like a low spatial resolution and low temporal resolution version of fMRI. And why is that? Well, if we take a look at blood vessels, astrocytes, neurons, post and presynaptic terminal, when we measure with fMRI, we are here at the level of the blood vessels, right? But when we measure with PET, we can be in many, many places, because we have many, many different targets which are sometimes related to what we measure with fMRI, but sometimes they are completely different. So it's an entirely different techniques that allow us to access very different things. And I will get to these a bit more in detail in 1 second. Now, I will speak a bit about the biological targets, spatial and temporal scale of PET. And most of the images I will show are from this paper. So if you want to take a look more in details, you can just download it. In terms of biological targets, so this is what we can measure with the other techniques. So with fMRI and fNIRS, we are the level of blood vessels. With MEG and EEG, we measure something that happens at postsynaptic level. And with structural MRI, we are again at postsynaptic or white matter level. With PET, we have, as I said, different tracers that measure different targets. Some, like perfusion and oxygen metabolism, is something, again, it's a target at the level of biological, at the level of blood vessels. We can get a bit closer to neural activity using, for example, glucose metabolism that you will see with XIN, which measures glucose metabolism in astrocytes and neurons as a marker, indirect marker of neural activity. But we get also directly at the postsynaptic level, measuring many different receptors and also enzymatic activity. And this data will be shown by Martin and Granville. And then we can also go at the presynaptic level, which is quite unique compared to the other techniques to measure, for example, neurotransmission, synthesis, reuptake, and production. Finally, we also have a series of receptors to measure pathology, for example, tau, amyloid pathology, which are very important for Alzheimer's disease, or neuroinflammation, which is important for many different diseases. We can also do more than this, of course. So more tracers can be developed, and we can measure more things eventually in the future. That's an evolving field, let's say. How to measure these things? Depending on the tracer that we are using, we might go for different types of acquisition. To start with, normally people do, with a new tracer, let's say, we'll go for a dynamic acquisition, which means we put with the person for a certain amount of time in the scanner. For example, if you do FDG PET, glucose metabolism, it would be around 60 minutes. So we inject, and we start to measure right at the beginning of injection. And during the scan, as I said before, you might want to take also, some blood sampling that might be needed for quantification, but it's not necessary for all tracers. For some tracers, however, things are a little bit easier, so you can have simplified acquisition protocols for what is called static acquisitions, which means that you inject when you are out of the scanner. This is an example of an injection room. Don't mind, there is an EEG on the head of this person, but it's not relevant. So we are in the injection room, we inject. This person was very happy to get a PET scan. This is the mom of my boss, by the way. So we inject, we wait for the tracer to be picked up by the brain. So this is the uptake phase. And only after that, we put the person in the scanner for 10, 15 minutes, depending on the scanner and the tracer. So this is a bit more, let's say, easy to use acquisition type in clinical settings, but it cannot be used for everything. But this differentiation between dynamic and static acquisitions is very important, because depending on what you're using, you might do some types of quantifications, but not others. And Alessandra will explain better. A very important point I would like to make is that we can image, right now, only one tracer at a time. This is because, as I said, all tracers, once injected, they emit their positron, emits the electron, and they emit photons, which are at 511 kiloelectron volts. So there is no way to differentiate, at least based on this, between different tracers. There is some experimental work going on, but right now we image one target at a time. However, depending on which isotope you are using, you can do, let's say, almost simultaneous acquisitions. So for example, you can acquire with a tracer bound with carbon in the morning, and then in the afternoon you can do another acquisition based on fluorine. So based on different tracers, you can still have acquisitions close by. Another thing you can do, if you have a PET MRI scanner, you can integrate a measurement with PET with a measurement with MRI. And you can also, if you have a PET CT scanner, you can add a measurement with EEG. So we are acquiring right now PET EEG simultaneous data. EEG doesn't interfere with PET. There is no magnetic field, so you can, with a standard EEG, you can quite easily do PET EEG acquisitions. Okay, so this was for the biological targets. Let's go to the spatial scale of PET. So the spatial scale of PET is not too bad. You can see here an example of a random cube with some voxels for structural MRI, in this case, with typical resolution of different modalities. And you can see here that with PET, in a relatively recent PET scanner, you have a resolution of around 4 cubic millimeters. So this is how this would like. And this is compared to fMRI and MEG. So we are not doing so bad. In biological terms, what it means is that when we look into a voxel from a PET scan, we are imaging an average of around 2 million neurons, which is a bit more than fMRI, where in one voxel we have 800,000 neurons, but still much more, let's say, precise than MEG, fNIRS, or EEG. So just to be very, very clear of how a PET scan looks like, this is not how a PET scan in the 2000s looked like. This is an image from 1998. Our images right now look a little bit better, so you can definitely differentiate between different structures. There is also some last generation scanners where essentially the scanner is a very long scanner, is a total body scanner, where the coincidences that are being produced by the tracer are picked up by a much larger, let's say, array of detectors, and this gives a much higher sensitivity, and you can achieve a spatial resolution that is much lower, even around 1 millimeter. How much can we go down with technological improvement where there is a physical limit, which is the distance that our isotope can travels in the brain before being annihilated, which for fluorine tracers, for example, is 0.6. So it's hard to go well below this because of the physics behind PET itself. But I mean, not bad, I would say. Another point I would like to make is that with PET, you can map essentially the whole brain. In theory, you can do it also with fMRI, for example, but normally in acquisitions, you don't acquire the full brain. You acquire different slices, but leaving a bit of space between one slice and the other, just to be faster. And with EEG and MEG, you cannot image, let's say, for example, the brainstem. And with NIRS, you are limited to around 2 centimeters from the scalp, 2.5. With PET, you can image essentially everything. And one point I would like to stress is that you image everything at exactly the same time. With fMRI, you acquire different slices, right? But you don't acquire all slices in the brain at the same time. With PET, you can do it. And I will add that with some newer scanner, you have a larger field of view, which allow you also to image some blood vessels, which is very useful for quantification for some tracers to avoid blood sampling. You can use the radioactivity measured in the blood directly from the scanner, but this is for later. This is also a representation of what you can see with PET. Essentially, as I said, you have a good spatial resolution everywhere in the brain at the level of cortex, subcortex, brainstem, and cerebellum. You don't suffer, for example, from distortions at air tissues interfaces like fMRI, so you can pretty much image everything. But, very important point, the fact that you can image everything doesn't mean that for every tracer it makes sense to, to pick every part in the brain. So for some tracers, the targets are expressed pretty much everywhere in the brain. So yes, you can do a whole brain study with glucose metabolism, with synaptic density. But for other tracers, like for example, dopamine receptors or transporters, the signal is much, much stronger in subcortical structures, for example. So for this tracer, one would need to, let's say, reflect very well whether it makes sense to go also in other structure. I know that these tracers are being used in some toolbox for whole brain approaches, but just be aware the signal to noise in cortical structures is definitely not as good as in subcortical structures. And of course, it's what you want to do, but just be aware that if there is no target, the tracer that you see is essentially noise or unspecific binding. So you need to think if you want to go there. Last point is about the temporal scale. So you might have heard that PET is not exactly the fastest technique ever. So you don't use PET to measure in itself alone very fast brain dynamics. You see here on a logarithmic scale represented the temporal resolution of the different modalities, having as reference fMRI. So for fMRI, I consider a resolution of 2.5 seconds, because more or less is the time that it takes to acquire a volume in the full brain, all slices. And this is 2,500 times slower compared to an action potential that more or less can be sent in 1 millisecond. MEG and EEG are, of course, much faster. And with PET, we are much slower. So here, I mean, it is a pretty huge range of variability in the sense that, let's say, it depends a lot on the biological process you're measuring also, but you have a temporal resolution in the best case of seconds, in the worst case of several minutes. And here I would like to make explain a little bit more what you need to think about when you say temporal resolution with PET. So in a static acquisition, as I said, you have 30 minutes of uptake, for example, for FDG, and then 10 minutes of scanning. And you get one image, and here is an example. So this image is an average, one single image, okay? There is no time here. It's one single image that is an average of what happened of what was measured, in these 10 minutes. But what was measured in these 10 minutes depends on really what happened in the uptake phase, because it's in the uptake phase that most of the glucose metabolism fixed in the brain. So you have a volume that is 10 minutes long, but what is reflecting is something happening over a longer process. When you have dynamic acquisitions, you scan for 60 minutes. And in this case, you actually have different frames. So you have different volumes for the different, throughout the duration of the scan, which might last typically just a few seconds at the beginning of the scan, and then you take longer volumes towards the end. And in this case, so you have indeed, the resolution is lower, but again, you take these images to do quantification, and in the end, what you end up with, it's still one single image that represents an average of everything that happened during this time. One important point to make is that the standard modeling in PET kind of assumes that the process you are measuring is kind of constant in time. So there is it's kind of, the point is there is not much sense in going down in temporal resolution, because anyway we are measuring something that's constant. For example, how many receptors are expressed. So as I said, the concept of temporal resolution is a bit different than what you might be used to with fMRI. Just a point to make is that for quantification, it doesn't hurt, definitely, to have a better temporal resolution. And with the new last generation scanners, you can have frames in the order of 0.1 seconds. That you can see here an injection done at the level of the leg, the feet, and how the tracer distributes here in the carotids and then in the brain. And this resolution allows you to have a more precise quantification. But in itself, you are not going to It's just for quantification. In the end, you still end up with one image. There is an exception to that, which is functional PET. In functional PET, what you do essentially is that you inject your tracer, not in one go, but you do a constant infusion of the tracer over time for the full duration of the scanner. So you have a constant amount of tracer being supplied in the brain, and what you do here, for example, with glucose, again, you can study how the tracer uptake varies in time during rest or, for example, during task. And in this case, you can use, let's say, frames of a duration of around 30 seconds. We've also a study, I think, by Sharna Jamadar with frames of 16 seconds. So this is the lowest that you can go, but just for you to know, these frames are a bit more noisy because, of course, the images look noisier than what I showed before because you have less time, less coincidences to detect. I'm not an expert in this, but if you want to speak more about functional PET, I invite you to go to the OHBM Australian booth and exposition room to speak directly with Sharna, and here is when you can find her. This is just a summary. I don't have time to go through all of these. Here you have a bit of the characteristics, the advantages compared to other techniques, and the disadvantages. One point that you might make is that there is, of course, it's a radioactive tracer, you have radiation exposure. In a FDG PET acquisition, at least in the protocol that we use at my center, you'd be exposed to around 2.5 millisievert, which is equivalent to eating 2,000 bananas. There is actually a banana exposure unit on Wikipedia, if you look it up. It's not little, but it's the same. To give you a reference, more easy to understand, is around the amount of radiation that each of us gets in 1 year of your life just because of background radiations. But still, I guess this makes the point that it's important to reuse these data as much as we can. Just to end, I would like to thank the people that are part of the molecular connectivity working group, which is organizing this symposium. Today, you will get to know some of them. It's just a group that studies, essentially, uses molecular imaging to study brain connectivity. Igor, which is the co-organizer, will not be here because there is a baby coming any minute, today or tomorrow, next week. So I invite you, if you're interested in molecular imaging and or brain connectivity, to follow our initiative. And tomorrow in the morning, there is also a symposium still of our group on the brain connectivity part of what we care about in terms of, let's say, validation, or let's say it's more a reflection about what we should be doing differently when we work with brain connectivity. If you want, just go to the website and subscribe to the newsletter. And with that, I will finish. Thanks a lot.